So today we're going to be doing special triangles. So special triangles is how you sort of connect an angle with trig ratios without using a calculator. It's just two triangles with designated angles and sort of nice ratios for side lengths. So the first one we'll be talking about is the 30-60 triangle. It'll look like this. This angle 60 degrees. This angle is 30 degrees. So for this triangle, the hypotenuse has a length of 2. Then the leg opposite to 30 is 1. The leg opposite to 60 is root 3. Thus, the trig ratios are simply the ratios. So sine of 30 degrees, if we take 30 as our reference, is equal to 1 over 2. Cos of 30 degrees is equal to root 3 over 2. Tan of 30 degrees is equal to 1 over root 3. Now for the 60-degree angle, you can also consider that as the reference angle. In that case, sine 60 degrees is equal to root 3 over 2. Cos 60 degrees is equal to 1 over 2. Then tan of 60 degrees is equal to root 3 over 1, or just root 3. Also remember that you should also know these in radian measure. So 30 degrees would just be pi by 6, and 60 degrees would be pi by 3. And we also have the secondary trig ratios, which can also be found, but they are just sort of the flipped versions of the primary trig ratios. So you just flip the fractions for the secondary ones. And now there's one more special triangle, and that's the 45-45 triangle. In this triangle, both of these corners are 45 degrees. Of course, this is 90 degrees again. Here, the hypotenuse is root 2, and both legs are just 1. So the ratios for this is pretty easy. Sine of 45 degrees would be 1 over root 2. Same with cos. And then tan of 45 degrees is just 1, or 1 over 1. And of course, this would be the same for both reference angles. So there's no extra set here. And again, you should know these in radians. So 45 degrees is pi by 4. And again, you can flip these fractions to get the secondary trig ratios. So now let's try to go from an angle to a ratio. Say we wanted to determine what cos of 5 pi by 6 is equal to. Well, let's draw out the angle in standard position first. Cos of 5 pi by 6, that is pi by 6 away from half rotation, so it's somewhere over here. And as I just mentioned, it's pi by 6 away from a full rotation, so this reference angle has to be pi by 6. So now we can consider pi by 6 in terms of our special triangles. So the one with pi by 6 is the 60-30 one. So here, this is pi by 3. This is pi by 6. This is 1, 2, root 3. So what is cos of pi by 6? Well, cos pi by 6 is equal to the adjacent over the hypotenuse, so root 3 over 2. But now we have to remember that the sign could change. So let's draw and cast. 5 pi by 6 is in this quadrant where sine is positive, so cos is negative. So therefore, cos of 5 pi by 6 is equal to negative root 3 over 2. And that's our answer. Now we can also go from a ratio to an angle, although this can often bring up multiple solutions. So say that if we are given that tan of theta is equal to 1, what would theta be equal to? Well, let's draw our standard position of the angles again. So first of all, one thing to note is that tan here is positive. The ratio is positive, therefore tan must be in this quadrant where everything is positive, or this quadrant where everything is negative. Now tan of 1 should cause you to think about a special triangle, namely the one with, let's do degrees this time, 45 degrees, 45 degrees. The hypotenuse is root 2 and the legs are 1. So tan of 45 degrees will equal to 1. So therefore, let's draw a line here. And here, this is 45 degrees. Of course, this is essentially a special triangle. This is 1, 1, root 2. But there's another solution because tan in this quadrant is also positive. Let's draw one this way. Hypotenuse is still root 2. This is negative 1, negative 1. And this angle here is 180 degrees plus another 45 degrees, which is 225 degrees. And these are two solutions within one rotation. So technically, there could be an infinite number of solutions for theta, but if we keep it within 360 degrees, there are only two solutions. So theta could equal 45 degrees or 225 degrees. So always be very careful with the restrictions on the domain, because if those aren't given, you have infinite solutions. And again, there is a way to represent that, but we won't be going over it. There are also more special cases for sort of these angles in standard position, and that is when your, there's a different color here, when your ray is actually on one of the axes. So say if your ray is here. Recall that sine theta is essentially equal to the y value over the radius. Why is that? Well, let's draw a really quick example in here right now. Say we take a triangle. This height here is always just the y value. And of course, r just stands for radius. And then this bottom length is always just the x value. So sine theta is y over r. Cos theta is equal to x over r. And tan theta is equal to y over x. Right? So when we have just a line there, we can just plug our values in. So sine theta, y is 0, would be 0 over r. And let's say we have a unit circle here, so r is equal to 1. So you'd have 0 divided by 1, which is equal to, well, 0. Cos theta would be 1 over 1, which equals to 1. And tan theta would be equal to 0 over 1. And that again equals 0. So these are the trig ratios for when this line is on the positive x-axis. And we can do the same sort of idea with this positive y-axis, which is a better color. Sine theta would equal, again, pretend I wrote in y over r, x over r, and y over x. But it would equal 1 over 1. Cos theta would equal 0 over 1. And here, tan theta, what would that equal? Well, the y value, let's say it is 1, but then the x value is 0, so it's 1 over 0. But that's undefined. So tan theta, when it's at 90 degrees, is undefined. And this same logic will apply to all the axes, except the signs will change. So for example, along this axis, sine will equal -1. Sorry, it'll equal 0 again. Cos theta will equal -1. Tan theta will equal 0 again. And then this axis, here, sine theta will equal -1. Cos theta will equal 0. And tan theta will become undefined again. So eventually you'll sort of know these by heart. And to help you sort of orientate yourself, so if you know the trig functions, those can help you as well. Let's draw an axis here. A sine function always looks like this for one cycle. Now see how it in fact starts at 0, right? This axis here. It goes to 1, this axis here. Goes back to 0, this axis here. And then goes to -1, this axis here. So it matches up like that. For cos, on the other hand, it starts at 1 and goes like this. And that again matches what we've been doing, where cos at this axis is 0 degrees is equal to 1. At 90 degrees is equal to 0. At 180 degrees is equal to -1. And then at 270 degrees, straight down, it's again equal to 0. And tan looks a little bit different, where the tan function will sort of look like this. It will create asymptotes periodically. Every 180 degrees. So here, tan at 0 degrees here, of course, is 0. Then at this sort of 90-degree point, it's undefined. And this tan function actually repeats like this. At 180 degrees, it's again equal to 0. But then at 270, it becomes undefined again. And this cycle just keeps repeating. So if you know the trig functions, those are really useful to consider when you're dealing with any sort of trig ratio involving 0, 90, 180, or 270 degrees.